Hello, my name is Thiago Americano do Brasil, and I'm going to briefly present the most important aspects of our paper called Detection of High Impedance Faults in Primary Distribution Grid Using Support Vector Machine Classification. This presentation is divided into 5 major parts. Firstly, we will briefly approach the scope, context, and objectives of this work. Next, we are going to discuss the methodology described in our paper. Section 3 presents the case study from which measured current data is collected, extracted, and used for training the supervised learning classifier. Finally, Section 4 presents both classification and detection results. Section 5 and 6 then presents our final conclusions and reference using this work respectively. One of the most problematic incidents in power distribution systems are the high impedance faults. This event represents hazard to people, animals, and overall physical infrastructure. As seen in these two photos, a high impedance fault across the distribution grid may be caused by direct contact with trees, for example, photo in the left, or due to the overhead conductor rupture, consequently touching the ground, photo in the right. So, due to the highly resistive characteristics of soil surfaces, the fault current possesses magnitudes close or even lower to the nominal levels of the feeder. In this way, the protection fuses along the feeder, as well as the overcurrent and residual relays at the distribution substation, are not often sensitized. Thus, their correct detection and consequent extinction are usually difficult tasks. One possible workaround proposed in the last 20 years was recording staged HIFs, using them to improve the overall protection relay performances. However, a series of restrictions have been currently imposed regarding the execution of these staged faults, as these can impose an additional and unnecessary risk on the rest of the power grid. Therefore, a mathematical modeling that precisely represents these faults is fundamental for research on HIF classification and detection. So the two major objectives of this work is, number one, provide a better HIF classification solution using the improved ARC model proposed by Wei, and number two, propose a HIF detection scheme using short-time Fourier transform, STFT, for filter extraction and support vector machines algorithm as the system classifier. To improve HIF classification model, a better understanding of its current behavior is needed. Beyond its low current magnitude and the accompanied arc, HIF usually presents several electrical characteristics, some of which are described here: asymmetry, randomness, nonlinearity, and intermittence. As already commented, most of the arc models presented in the literature usually only consider stable arc ignitions, disregarding most of the characteristics inherent to the HIFs mentioned above, mainly the intermittence and the randomness. It is unlikely to obtain a robust classification system and detection of high impedance faults. This issue can be amended by inserting a random coefficient to the conventional Meyer arc model. Overall randomness and intermittence probability can be achieved through the selection of parameters K1, K2, K3, and K4, P loss B and P loss 0 accordingly. The following picture presents 3 different type 1 HIF characteristics that were recreated in SimPower systems in MATLAB from waveforms already established in literature using the improved ARC model. Analogously, this picture shows faults that present unstable behavior, especially when compared to type 1 HIFs. HIFs that only possess fluctuations randomly distributed along the current waveform are labeled as type 2A. On the other hand, HIFs that in addition to random fluctuations also present overall intermittence are classified as type 2B. When extremely high grounding impedance are present, some HIFs may depict type 3 behavior. Thus, fault current amplitudes tend to be much lower. Therefore, its waveform might exhibit high-frequency distortions due to the existence of white Gaussian noise. Regarding the classification scheme, some questions must be answered. What are the measurements in data collection stage? How the classification stage will be able to differentiate a HIF and a non-HIF event? These answers to these questions are given below. The monitored variable is the residual current, which is the sum of the currents from phases A, B, and C. The short-time Fourier transform is used for the feature extraction stage and is responsible for dividing a signal into several smaller segments of equal length, deploying the conventional Fourier transform on each of these segments individually. From there, the feature extraction obtains new features from transforming its original input signal. On the other hand, the feature selection is achieved when a certain number of relevant characters are chosen. In general, it is important to consider the use of the lowest number of characters as possible. The developed systems must be able to distinguish HIFs from other transients of common occurrence in a distribution system, such as inrush currents, capacitor switching, and load switching, for instance, to avoid false tripping. This stage is performed by the SVM classifier. Feature selection was carried out considering the normalized spectral contents of each type of fault current, type 1, type 2, and type 3, present starting from 0 Hz, DC component, until the 25th harmonic order, 1.5 kHz. The normalized spectral contents of each type of HIF are presented in this picture. Type 1 faults tend to feature more restricted harmonic content, whereas type 2 and 3 exhibit significant harmonic content even after 540 Hz. The main SVM objective is obtaining the finest separating hyperplane through enhancing the margin between this hyperplane and overall feature selecting output data. This paper proposes a nonlinear Gaussian kernel function, and the SVM algorithm is intended to classify only two distinct classes, labeling them as HIF or non-HIF in a one versus all manner. The picture below depicts the diagram of the 20 kV distribution test system simulated in the SimPower system environment in MATLAB. Taking into consideration that in MV distribution systems, loads are generally fed by a step-down transformer, in which the MV side is usually wired without neutral lines, the residual current measured at the MV terminals, the measuring point, is almost unaffected by the loads present at the LV sides. Non-zero values of residual currents can be attributed to load transients, earth faults, or normal transient phenomena along the feeder. As mentioned before, an effective SVM classification is required in order to distinguish between HIFs and the daily common transients already mentioned. The training set is established through several conducted simulations in the 20 kV test system presented. 6 types of power quality transients were considered: single-phase capacitor or load insertion, two-phase load insertion, three-phase load insertion, three-phase low load transformer insertion to attribute the current inform events, and obviously HIFs. Besides, all current measurements were carried out at the measuring point, and the events were executed one by one, only in feeder F1 at a random point L that ranges from 0, the beginning of the feeder F1, to 45 km, end of feeder F1. To achieve the forecast model, 100 5-second simulations were brought about, with each of these containing approximately 10 random events, which comprises a total of 1,000 discrete phenomena, where nearly half of them consisted of random HIF occurrences. Each simulation extracts its feature through the use of STFT, dividing them as HIF or non-HIF events, and gathering, labeling HIF or not, and features information into a single matrix, as depicted by the flowchart. The summary of the simulated events, including HIF, as well as their respective ranges, are presented in the tables below. After obtaining the forecast model based on the training proposed in the previous section, a detection system was developed considering an estimate of the probability of recurrence of a HIF event. Basically, the residual current is acquired and its main spectral characteristics are extracted using an n-length window in the same way as performed in the training process of the SVM classifier. Thus, the classification states of each window can be 0 non-HIF or 1 HIF. To improve the optimization of the detection process, a sliding window strategy was used, where each analyzed window presents an overlap of 15% in respect to the previous one, to avoid spurious alarm due to the presence of short-term transients whose spectral characteristics may be similar to those present in HIFs. A temporal consistency of each detected event was verified. The flowchart of the right depicts the algorithm proposed for HIF detection, with the image on the left side representing an example of a correct detection. To train the classifier, the selected set of features comprising its classification were fed into the classification learner toolbox in MATLAB. To analyze the results, STFT was applied on residual current considering two distinct window lengths, 2,500 points or 360 Hz cycles and 5,000 points or 6 60 Hz cycles. Likewise, the selected features vector was also varied considering the aforementioned covered range. In this paper, SVMs were based on optimizing and its accuracies were obtained through 10 cross-validation folds, estimating accuracy on each fold individually. The following table presents the obtained SVM classification results considering a window length of 2,500 points, which present the best results. To verify the reliability of the detection stage, a cross-validation system was created. The occurrence of each transient phenomenon occurred individually, based on 20 random simulations that lasted 5 seconds, totally 173 different events. That is, the insertion of a new transient phenomenon occurs instantly after the removal of the previous one. Each of the events occurred at a random position L along the 45 km feeder. Besides, the choice of the phase A, B, or C, where each event took place, was also randomized. The following table shows the confusion matrix of each of the results obtained regarding the occurrence of each transient phenomenon individually. It is possible to verify that all type 1 and type 2 HIFs were successfully detected. On the other hand, the detection of type 3 faults was slightly compromised, in which 10 out of 12 faults were accurately detected. This is due to a primary factor. The low amplitude of the current from type 3 faults makes the distinction between these faults and an event that causes imbalance very difficult. An important aspect of the detection strategy proposed in this work was to maintain a fault detection rate higher than 90%, while no transient event was configured with a HIF. This shows that feature extraction and selection were both properly conducted and that a significant classifier's generalization capability was obtained. So, we conclude that the present work showed that a precise feature selection stage is crucial not only for the decrease in computation and efforts of the detection test, but also considerably improved the SVM generalization capability, and the proposed detection scheme can be effective for monitoring HIF occurrences in real-time applications. Type 1 and Type 2A faults were readily detected. On the other hand, Type 2B faults may be troublesome, especially when present long intermittence periods. So these are the references used in this work.